In this video, we're going to show you examples of plotting probability distributions of the discrete and continuous type in SMath Studios. For that, we're going to use the definitions of probability distribution and statistical tools and graphics of the plot XY type, as well as snippets that are available in the description of the video or in the description of the previous video or video number 517. With that, we'll continue with our SMath Studio file. The first step is to insert the two snippets. The snippets have been downloaded and are available to insert, and the ones that we need are S&G information, S&G information, and the next one is S&G functions. Under S&G information, when we open up and we go into probability distributions, we find here this segment that talks about graph of PMS and CDF for discrete distribution. These are the only ones that need any particular type of functions, because the continuous distribution is as simple as typing the names of the functions and using a plot XY. For graph of PMS and CDF, we need to define those PMS or CDF for discrete distributions, and then we need to define a column vector of the values of x using the function range. For example, x range from 0 to 10 in increment of 1, or produce the vector of values of the probability mass function and the cumulative distribution function as functions f of xx and uppercase f of xx vectorized. Then we create a matrix that consists of putting together the values of x and f, insert a plot XY graph, use the matrix as the graph entry, and adjust the grids as desired. To plot the CDF is a similar situation. We have estimated or calculated our vectors of FF, form a matrix, use it as entry for the graph, and adjust the grid ranges. Here are some examples for you to consider, but I actually have better examples in my page here, so I'm going to close the S&G information, and the S&G function is what includes the function we're going to use. For example, in the binomial distribution with n equal 10 and p equal 0.4, we create our vector x from 0 to n, and then vectorize. Remember, to do this, we just do ff column pdf dot binomial xx comma np. Then do a space bar to select the right hand side, and then go to vectorization right here. We need to go here to calculation, make sure the auto calculation is on, and then it starts producing the graph. The functions that we use to produce the matrices of plots is called plot PMF for the probability mass function. I'm going to move this over here, and plot CDF for the cumulative distribution function. And they produce this type of graph. The probability mass function is called mass function because the probability is like a mass that is concentrated around every point, whereas the cumulative distribution is such that whatever value you have at this point remains like that until the next point is found, in which case it increases and then increases again, but it remains constant until a new point is found. And so this is the typical graph of the probability mass function and the probability density function. I'm going to do another case here. For this Poisson distribution, we use the parameter lambda equal 1.2. And the Poisson distribution, the values of x actually go to infinity, but we selected 10 of them only. And we have created our vectors of probability mass function and probability cumulative distribution function. Create our plot matrices for the mass function and this cumulative distribution function. And this is the way those values are plotted for the mass and the cumulative distribution. Function, you gotta be careful with the mouse wheel right there. Geometric function has a single parameter, and again it also goes to infinity, so I selected 10 points, created my points for the probability mass function that the plugin called it probability density function. And then for the cumulative distribution function, create the matrices for xx and ff, and this is the graphics for the mass function and the cumulative distribution function. Here's the case for the uniform discrete with values of m and n 14, 8 and 14. Here's how you create your mass and cumulative distribution functions, create the graphics, and produce the plot. A uniform distribution means that the probability is the same for all the values where the probability is valid. So it's pretty much a constant value here in every point. And then the growth is sort of in a linear fashion, remaining constant until the next value is found. For continuous distribution, it's very simple. Basically, you have to define your function. You have to define your functions here, and we just need to define the functions. We don't need to produce point values, and just enter f of x or uppercase f of x as the entry point for our graphics and produce the distribution. You just have to adjust the x and y axis so that the distribution will be visible. This is the case of the Cauchy distribution. Here's a normal distribution. It's very symmetric, so it's the Cauchy. And the typical cumulative distribution function graph for continuous distribution is this S-shaped figure. Here's the Rayleigh distribution that's only defined for positive values. The Weibull distribution, there is no, although it is listed, for some reason it doesn't work. It's not well defined in the plugin, but the textbook definition is this one, and so I redefined it there, so I can define my f of x, and I'm able to produce the Weibull PDF and the Weibull CDF. Oh, gotta be careful there with the mouse wheel. For the uniform distribution, I got a uniform distribution between 25 and 110, and I put it in the vertical starting negative so I can see that going from 0 to a constant uniform distribution down to 0 at the upper end. And the cumulative distribution function is actually a straight line, but it always has that S-shape characteristic of continuous distributions. The student T distribution is used in probability inference, in statistical inference, sorry. And there's your PDF, and this is the CDF. So the chi-square, it turns out the chi-square, also the plugin has a fault in there. The cumulative distribution is not defined. However, for all practical purposes, this is not necessary, because when we use the student T, the chi-square, is for statistical inference. We're looking for the inverse cumulative distribution, not for the cumulative distribution. So that works okay. The F distribution, finally, is also one of the continuous distribution, and here's an example of that distribution. And with this, conclude these examples of plotting probability distributions.